Welcome again. And this is Introducing Graphing Techniques. It's a lab that we're going to perform outside the lab environment, because graphing is something that you do after you have the data that you've acquired in the lab or in the field or wherever it might be. But let's get down to business. The Introducing Graphing Techniques, I'm going to approach this in fairly logical steps. We need to know a purpose. What's the purpose? I mean, why are we doing this? Besides, the instructor says so and you need it to get a grade. Then we're going to look at the parts of a graph, and we're going to be specific to the two-dimensional arena, the Cartesian system. Then we're going to look at best parameters. That is, how do you build the graph in the most efficient manner? Use the space most efficiently. And for instance, you don't have a lot of empty space where there's no information. Then what does the graph mean? We need to know what the graph is trying to say, because we're saying it to our reader. Okay, so what I'm going to do is share the document that you're going to be using to conduct the experiment. Here we go. Now, for the moment, I'm just a little thumbnail up in the corner. That's all right, because I'm going to edit this video so that you can see both me and the document. And I need to do that because I'm going to pull out another whiteboard and use it to draw a graph. Okay, so let's look at the purpose first. Why do you need to even graph your data? If you have numbers, data points, values that you've determined in an experiment, sometimes you can present that data to your reader in your report as a table. If there are a small number of values and they're sufficiently different from one another so that you can make your point, and that's the whole purpose of a publication, is to convince your reader of your position. And sometimes presenting the data in a simple table is all that's necessary. But other times, you may want to argue a position and I want to be sure that I'm recording this. Pause for one moment. Yes. Those of you who have taken any of my courses other than this one know why I'm paranoid. Sometimes I have a tendency to start the presentation without starting the recording, but we're recording. That's good. Okay, so back to the point. You're trying to convince your reader of your position. Sometimes visual impact is valuable, and one way to do that is with a graph. Now, there are a whole host of different graph designs that are used to present data. We're going to start with the very simplest one, and simple is always better. If you can keep the graph presentation simple and get your point across, that's the best way. Only go more complex when the data and your argument demand it. So we're going to be looking at the Cartesian system, which if you've had a math course, we'll understand that it's just an XY system. All right. So let me put this down for the moment. And let's look at the Cartesian system, otherwise known as a graph. Oops, too far. Here we go. Sometimes we're called a line graph. So I need something a little larger than a ruler, but not too big. Pardon my absence. Well, we may be stuck with a ruler. Let's just make do. So our Cartesian system, here would be a horizontal line. The x-axis, or the abscissa. And then the y-axis, like that. That's also known as the ordinate. Notice that what we've done is this field has been divided into 4 parts, quadrants. So we have a quadrant here, 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 here. Now, what are the characteristics of those quadrants? Well, in any Cartesian system, if you apply a point anywhere in the graph, that point can be identified by how far is it on the x-axis, and how far is it on the y-axis. So this one would be over this many units on the x-axis and this many units on the y-axis. That identifies that point in that 2-dimensional space. Now, the characteristics are, and by convention, these are all positive values of x, and these are all positive values of y. Anything down here is negative value of y, and this one is negative value of x. So it's possible and often used when you put a point anywhere in here. This one would be, say, here, would be a negative x and a positive y. Okay? Sometimes you do need to use the negative side of the graph. And one of the problems that you're going to work on in this exercise makes use of the negative side of the axis. Okay, so that's the basic Cartesian system. By the way, if we put a point there and it represents something that we've done in the experiment, what does it mean? Its relationship to the experiment is that point is a measurement that was taken during the experiment. That's what the point means. All right. Okay, let's say you have a set of data, and it might do well to actually use the data from our experiment. Or we could use this data. This would be fine. Okay, let's say we have, no, let's not use this data. You can study that on your own. I think I'd rather use let's use data Come on, it's being stubborn. There are delays. Okay, let's go down to, notice while we're here that the data can either be, if you put more than one point on a graph, they could be in this relationship, 1 point down here, 1 point up here. Or they could be 1 point here, and then you go down to the next point. And those are two different types of relationships. This is a direct relationship. This is an inverse relationship. And that's characteristic of any graph. If the slope of a line is positive or to the right, it's a direct relationship. If it's negative or to the left, sloping from upper left to lower right, then you have an inverse relationship. Okay, so let's actually look at some numbers. Okay. It's okay. Let's see. Those, you can answer those questions yourself. Here we go. So let's take this data set. First of all, when you're doing the experiment and when you're expressing it in graphical terms, you need to identify, these are variables, means they can change. Temperature here versus volume. Those are variables. In the Cartesian system, the x-axis is reserved for the independent variable. So let's draw that again. And let's say, let's put it down here this time. Let's say our 0 point is going to be here. So what does that mean? That means if you put a point there, its position is 0, 0. So this x-axis is going to be like that. Okay, and it can go negative. Now, why am I doing that? Why am I making a place for negative values? Because temperature can go negative in this data set. But why would I say negative on this axis and not the y-axis? Because I'm identifying the independent versus the dependent variable. So which is the independent variable? The independent variable is the one that the researcher changes. So I set the temperature at each one of these points, 0, 50 degrees, minus 50 degrees. I set that in the experiment. The dependent variable is the response in the experiment to my independent variable. So when I change the temperature as the independent variable, I get a response in the volume of the gas that's being measured. So when I increase the temperature from 0 to 50, notice that the volume increases from 5.6 to 6.53 liters. So let me say that again. The independent variable is the one that the researcher controls. And the dependent variable is the response in the experiment to the change that the researcher has made in the independent variable. So that's why the x-axis is reserved for the independent variable, which in this case is temperature. So you identify that axis as temperature, and the units of measure. If you identify the axis as temperature without the units of measure, it means nothing. It could be Kelvin, it could be Fahrenheit, it could be a made-up system that we know nothing about. You have to put the units there. Otherwise, the labeling is incomplete. Okay, so now we're going to go with the rest of the graph, which is the y-axis, or the dependent variable. Let's go up a little more. Okay. Now, why did I go all the way to the top? The reason is, in your graphing system, you want to make full use of all the space you have available. Now, this axis is going to be the dependent variable, which is volume. So what is volume? Units, liters. There, we've identified the parameters for this one. These are positive, these are negative. Those are all positive. Why? Because the data says they're all positive, 4 to 7. Okay? All right, next thing you have to do is decide, we've decided what the units of measure are. We just haven't decided what each one of these squares represents. Right? So the best way to do that is to go for the maximum. How far does the temperature need to go? It needs to go up to what? The maximum temperature is 100 degrees. So let's see if 100 degrees will fit on that scale and still give us 50 degrees on this scale. So if we do 100 here, notice we've got a heavier line there, which is kind of in the middle. Right? We've got the same number of squares, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So I would suggest that if we go all the way to the end at 100, then halfway this way would be what? 50. Okay? So that means if this is 50 positive, then the same number this direction would be negative 50. Right? You can't just arbitrarily change the scale. If you want to put 50 way out here, then 50 has to be the same distance on the other side too. There has to be balance. Okay, so we've got our major divisions. Now, what are the subdivisions? The subdivisions would go 1, 2, 3, 4, 5. So if we take 5 squares to get to 50, what does each one of those squares represent? 10. Each one is 10. 10, 20, 30, 40, 50. Okay, so you can mark it that way. 10 to 50, 60, 70, 80, 90, 100. So this is what we would call major tick marks, minor tick marks. Okay, so the other side would be minus 10 down to minus 50. Okay, so we've got this scale set up for our independent variable, temperature. How about volume? Well, the volume is going to go from 4.58 up to 7.66. Okay, so you can't very well assign fractionals to each one of these tick marks. So we've got to include all of these values in the space we have available. Look at the maximum. What would the maximum be? Well, if we're looking at whole numbers, the maximum would be, the nearest would be 8, rounded to 8. So let's see what 8 does for us on this graph. Let's see how many units we have. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, 16 would be nice because then we could use 2 units for each. 1 for 2 units, and 16 would make it 8. But we don't. So let's make do with what we've got. If we say each one of these units is 1, then that would be 1, 2, 3, 4, and this would be 5, 6, 7, 8. That's as much as we need. We go up to 10. Okay? So we're trying to use this graph the most efficient way. All right, now let's pause for just a second. This graph is built on a whiteboard. It's symmetrical, it's a square. But when you publish your information in any journal, the format of the journal is such that you could either have portrait, long end up, short end, side to side, or landscape. And that's a valid way to present your data, even on a regular page. The graph could be on a portrait page, but landscape orientation with the longer axis on the bottom, the shorter axis on the top. So I would argue that since this is the longer axis, we're actually building this in landscape format, right? Because this is the short one, this is the long one, right? It's like 8.5 by 11 would be the standard page size. So this is landscape. That's one of the parameters that you need to consider when you're building a graph. Do you want it to fit this way or that way? Okay, so if this is 5, that means each one of these is 1, right? The subunits would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to be within 8 on this scale and greater than 4. So it's going to be squeezed in here. Okay, we can't help that. That's just the way the data falls. If this is going to be 0, 0, then we have no choice. Okay, let's start putting our data points up here. Let's start at 0. Okay, so here's 0 right there. Temperature here. And then we're going to go up the y-axis to 5.6. So this data point is going to be 0, 5.60. So there's 5. This is 6, so it's going to be a little over 6, right in here. That's our first data point that we've put on the graph. Now we're going to have some going this way and some going this way. So let's go positive first. Let's say for the next one, we're out to 25 degrees. Where's 25? 10, 20, 25 is here. So we're going to go up until we find the y value, which is 6.12. Up here, that's 6, right? It's 5, 6. 6.1, we should put it right about here. Okay? Notice that when you draw it by hand, there's a good bit of estimation, right? So that's a potential place for error. If you get a computer program to do it for you, such as in Excel, you can put your values into Excel and it will create a graph for you. That's a different lab. We don't have time to do that one here. But if you're proficient with Excel, then you can do that. And you remove the error, the visual plotting error that we're introducing now. Okay, next, 50 degrees at 6.53. So 50 and 6.53 is about right here. Okay? We're doing what's known as populating the graph with our data points. So at 100, it's 7.66. 100, it's 7. There's 5, 6, right about here. There you go. Okay, now let's go negative. Negative 10 degrees is 5.5. So negative 10, there's 5. That's 5, 6. This is 5, 5, right in the middle. There you go. Let's see. Negative 50 degrees, 4.58. So negative 50, 1, 2, 3, 4.58, right about there. Okay, So now we have all of our data points on the graph. What do you do with them? Well, we could just leave them sit there, but the visual effect would not be quite as impactful. And there are other things that we want to know about this data that we will present in our report for whatever reader. One of the things we can do is determine, does that look like a curve of some kind, or is it more closely resemble a straight line? Well, all you need is a straight edge, right? Looks to me like it approximates a straight line. So, how do you apply a straight line to this and say that it represents those data points? Well, first of all, you have to recognize that there's always error in a measurement. Okay? So these points are probably not going to fall directly on a straight line. They're going to be off by just a little bit. So when you apply a straight line as an estimate to the trend, you want to minimize the difference between the line and the data points. Okay? In statistical terms, those are called least squares. Least deviation from the line is your best fit line. So I wish I had a longer straight edge to do this. Well, we'll have to make do. Okay, and it would be better if it were transparent, then you could see lines that were covered up. But if you try, if we just connect these 3 points, what does that do for the rest? Well, that puts the line way down here below these. That's not quite the best line. So we want to start in the middle probably and say, all right, so let's say that's about right. So let's look what it does for the others. It's pretty close to that one, close to this one. It's adjusted just a little bit. Now let's draw our straight line and see how good an estimate it is. All right. So we'll extend this line a little further. And extend this one a little further. All right. So there's another source of error because this probably should be tilted up a little bit to be closer to that one and bring this one down. Okay? But this is just an estimate. Now, what have we done? In between this actual data point and this actual data point, we have conducted what's called interpolation. We have interpolated on this straight line between and among known values. If you go beyond, like we did here and here, if you keep going, that's called extrapolation. X meaning outside of, interpolation. Inter means inside of. So inside the points, we're interpolating. Outside, we're extrapolating. Okay, so this is probably a straight line. And what do we know about straight lines? They have the same slope everywhere on that line. And how do you determine the slope? Well, you fit the curve to the straight line algebraic expression, which is what? The way I learned it was y equals mx plus b. Right? So this is your x variable. This is your y variable. This is the slope of the line. It's rise divided by run. How high does it go this way for every unit this way? And this is the y-intercept. So it's that point right there. That's what B would be. So how do you do that with points that don't land directly on that line? Well, it's not easy. There are statistical methods for doing that. but we can have a pretty good estimate. If we adjust this line to say, tilt a little bit to get close to that one and close to this one, we could say, okay, we're going to assume that this marks one end of the line and this marks the other end of the line. And in order to do a calculation for slope, we just need to say this is the run from here to there, and this is the rise. Right? So the slope is equal to the change in y divided by the change in x. Like that. So let's identify this point with a label. Right? So we can go from that. So this one is our minus 50. Here is x, and y is 4.58. So this one is minus 50, 4.58, x and y. This one is the other end. So the x is 100, and the y is 7.66. Okay, now we know, here are our y values, 7.66 minus 4.58. That's our delta y. Delta x is this one minus that. 100 minus a minus 50. Okay. So we actually have, let's see if I can do this in my head. This is 8, 5, 0. See if that's right. Add it back to this 16, 1 and 5 is 6, 3 and 4 is 7. That's good. Now this one is a minus is a plus. So that's 150. Okay. So what is the slope of this line by our method? All right, I need my calculator. What do I do with it? All right, so 3 point, I probably should have used my calculator to do the whole thing. 3.08 divided by 150 is, we could write this in standard notation or scientific. Let's put it in standard for here. 0, 2, 0, 5. 3 significant digits. Okay. So that's the slope of the line. What's the y-intercept? Okay, we have y equals 0.0205x plus b, right? So we need values for x and y so that we can determine b, because we can't solve this equation unless there's only one unknown. So the best way to do that is to use one of the points that went into this calculation, either that one or this one, right? If you try to use one of these, it might not fall on the line, right? So it would bias your data toward that point when you were actually using these points to construct the formula, right? So let's pick this one. So let's say y is 7.66. There's our slope. And x is 100 plus b. Then solve for b. So 100 times that is 2.05. And then we need to subtract it from this side. And that's 2.05 minus. So B is 5.61. So does that look reasonable? 5.61 is the y-intercept. Look here, there's 5, there's 6. So it's pretty close to 5.6. All right. So what formula, what equation represents the line the way we've constructed it? We would write y equals 0.0205 x plus 5.61. Right, now we have a formula for what we consider to be the best fit line for that set of points. And that would also be reported with the graph when you published it. What can we tell from this right here? We can tell that this is a positive slope. A positive slope means lower left, upper right, that direction. That's a direct relationship. What does that mean? That means that as temperature is increasing, volume is also increasing. Okay, that's a direct relationship. Okay, so we've worked that one out for you. You just need to answer the question. Okay. The next one is pressure volume. I'm going to let you do that one yourself. This one is a little trickier, and I'll tell you up front. Pressure volume relationship is a curve. And it's a curve that you cannot determine the slope for the curve unless you know calculus. Because with a curve, any type of curve, what's the slope of that line? Well, it depends on where you are on the point on the line, right? The slope might be that for that one. It might be this for this one. It might be that for that one. So it has a changing slope. And scientists hate that. We hate curves. When we can get a straight line, we go for it. Now, part of this procedure is to transform some of the data, pressure volume, transform some of the data so that you produce a straight line. And it's right in here that you do it. So which one are we going to transform? Well, I'm going to sort of generalize for you. You're going to have to draw it, but I'm going to generalize to help you along with the process of pressure volume. I just have to make room for it, is all. But I shouldn't erase that. I'm going to need that graph. So let's put that back up here with my ruler. I'll tell you what, I'm going to redraw it. And it'll become obvious why in just a second. All right. Okay, let's move this over. Reposition it. There we go. Okay. So let's look at this data for pressure volume. Notice what's happening here. Pressure and volume are changing. But if you're the experimenter and read the problem, the temperature of a 32.1 gram sample of methane was held constant. Right? Its volume was measured under various pressure. Aha, there's the clue. The volume was measured after the pressure was changed several times. So what does that mean? That means that the researcher changed the pressure. That's the independent variable. And the volume was the response, or the dependent variable. So which goes where? Pressure goes on the x-axis, volume goes on the y-axis. Notice something else. All of these values are positive. So which quadrant of the Cartesian system are we working in? Well, we had it labeled in the A quadrant. So over here, where every x value is positive, every y value is positive, we can just move everything over here and start our 0 points right there. Okay? All right. So let's use as much room, as much space as we have available. There. This is our 0, 0 point. And what did we say goes on the x-axis? The independent variable is pressure. And what are the units? Look at your table. Units are atmospheres. That leaves volume for the y-axis, measured in liters. Okay? So now we need a scale. So what's the scale? Look at your data. Pressure goes from 0.5 up to 3.5. So let's say for whole number, we need to use whole numbers when we're setting our scale. So we're going to go from 0 up to 4. Let's see if that can fit in here easily. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15. So I've only got 15 squares. 4 would be easily divisible into 12. Right? It would have been better for 16 if I had 16 squares. So at this point, you could redraw your graph. Just move this over one, and that puts 16 out here. And that gives you room for 4 major tick marks at 1, 2, 3, and 4, and then 4 minor squares inside each one. But that's okay. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So at that point, we're going to call that 4. That means to get 12 squares into 4, each one is worth a third. Right, so 1, 2, 3. This would be 3. This would be, let's see, let's do it this way. 1, 2, 1, 2, 3. There we go. So that would be our x-axis. Y-axis goes from 97 down to 14. So if this is 0, 0, we're only concerned with the maximum value. So 97, the maximum value would be best chosen as 100, I think, rounded off. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So how does 15 go into 100? 6.67. That doesn't work for me. What if we made 10, 20, 30, 40, 50, 60, 70, 80, 90, 100? If we made that one 100, then this one would be 50. Okay? And each one of these would be 10 liters. That seems reasonable. Okay, now I'm going to let you put the points on your graph. I just helped you out here. But what does the shape look like? The shape looks like landscape. Short here, long there. But if you have the right paper and you move this down, then you could stretch this out further. And this would be the long end, and this would be the short end. Portrait. Right? So you do have some leeway in choosing your format. You just want it to look convincing. All right, so I'm not going to draw the points, but I'm going to tell you what the shape is like. Notice first what happens. As the pressure goes up, what happens to the volume? The volume goes down. That means that as the pressure goes up, this one goes down. So for each point here, this comes down. Okay, that's an inverse relationship. And it's going to look something like that. Okay? It's a curve. It's a special kind of curve. It's known as a hyperbola. So those of you who remember your math classes, what is a hyperbola? Well, hyperbola is a conic section, and I won't go into what that means. But it also means that this tail and that tail never touch the axis. They go out to infinity without touching the axis. That's characteristic of a hyperbola. Okay. But it's not a straight line. So how would you make a straight line out of this data? Well, we haven't talked about Boyle's law yet, which is what this is. This is Boyle's law. But when you get to the gases, or when we arrive at gases in the lecture part of the course, what you will find out is what Boyle said, and he proved it with experiment, is that when you multiply the pressure value times the volume value, you get a constant. So whenever the pressure goes up, volume has to go down in order to keep this product equal to K, or the constant. Anytime you see one variable times the other variable equals a constant, that's always an inverse relationship. Our previous experiment, volume and temperature, that relationship is that, a quotient. Whenever you see the quotient of two variables equals a constant, that is a direct relationship. And it will have a slope like that. Whereas this one will have a slope roughly leaning that direction. But this particular relationship is always a hyperbola. Okay. So, is there a way to make a straight line out of that? Well, let's look at the algebraic transformation of that formula. This is a constant. These are variables. So, is it valid, algebraically speaking, to divide both sides of that equation by one of those variables? And the answer is yes. If we divide this side by volume and this side by volume, we have not committed any errors, algebraically speaking. So what happens on this side? Volume cancels, right? So what do we have now? We have P equals K over V. How does that help us? Well, I'm going to tell you in just a second. As soon as I get this frog out of my throat. All right. So notice that we can also separate these two on this side. And what that looks like is, this is K here, and this is 1 over V. right? Is that valid? Well, go backwards. K times 1 is K. So K goes up here over V, and there you have it. So I haven't committed any errors, right? Notice what else. What does this look like now? This looks like Y equals M X. Uh-oh, where'd B go? If this is a straight line, we have a y-intercept, don't we? Right? So what's B? B is right here. B is 0. That formula goes straight through the origin. Okay? Now, when we do these transformations, the concept of inverse versus, the concept of dependent versus independent variable, we have to make allowances. Because with this structure, that puts P on the y-axis and 1 over V on the x-axis. And that's okay. Because we started from this one as independent variable, dependent variable. Okay, so that's what that transformation in your problem is talking about. Let's see. We're going to go down to express the data in a different way. Expressing the data in a different way means converting all of your volume measurements to their inverse. So just set up your table or go up here, right, and write 1 over V right here, and then take the inverse of each one of these volumes and put the numbers right there. Then you're going to plot P against 1 over V. Right. So you need a new graph. You could put 1 over V over here, that's fine. It just wouldn't fit with the Y and X thing. This would be X and that would be Y. And that's not a problem either, because either way you put it, whether it's inverse V down here or inverse V up here, you're still going to get a straight line. And you can prove it to yourself just by plot the data. Plot pressure against 1 over V, or the inverse of V, and see if you get a straight line. Now, what are the units of measure for 1 over V? Right? So wherever you put it, if it's 1 over V, what are the units of measure? Well, remember, when you take a variable and transform it, you don't just transform the number, you transform the units also. So what would be the units, the inverse of liters? 1 over L? Yeah? But we have another way of writing that. 1 over L is equal to L to the minus 1. Okay? So your units would be L to the minus 1. Liters to the minus 1. That means inverse liter. Okay, so I've given you everything you need to graph this one. And let's see if there's anything else. Now we get into a bonus section here. This is entirely up to you. What you're going to get into with the bonus section is multiple curves with your data. If you actually plot this titration curve and we identify the volume of base added here is what the researcher does. So that's the x-axis. Down here. The pH of the reaction is here. It would go there. And then you would plot your points and then try to draw the best fit line. I can tell you right now that the best fit line is not going to be a straight line. It's not going to be a simple curve. It's going to be a compound curve, something like that, an S-shaped curve. So if you want to do this one, then you're probably going to have to hand draw the curve in, because it's difficult to get software to do it for you unless you have a specialty software. But Excel, you really have to do some manipulation to get Excel to do it. In fact, you have to set up 3 different data sets and have the curves drawn independently. So I'm not going to burden you with that. Just do it by hand for a best fit line. There's another set of data, and let's see. There we go. There's some delay. And now, in the printed hard copy of this method, I've incorporated graph paper. So there's one. This one would be for like the volume and temperature. And then I skip a page so that if you print it double-sided, then you won't print back-to-back graphs. This one you could use for pressure times volume. And then this one you could use for pressure by 1 over volume, or inverse volume. And then I have some others that you can use for the bonus or extra credit section if you decide to go that route. Okay. Also, in Blackboard, there should be an item in with this hard copy that says graph paper. So all you have to do is download that file, and you can print out more graph paper if you need it. Okay, so let's see, have I covered all my topics? I believe so. I think we've got all the topics done, and you just need to draw the graphs. Don't leave anything out. One thing that we did leave out, okay? Think about if you're going to publish your data in a referee journal, which is what you should be thinking while you're doing this exercise. If you were going to publish it, one rule, hard and fast rule in any publication is all figures and all tables for that matter, but all figures, which is another word for graphs, have to stand alone. So when you see in the publication, you see a graph, it's going to have a title, which the title may be down here, and it's going to have a description. And then all this other information, so that anybody looking at that table independently, or that graph independently of the article, can see what it's trying to say. Now, that may not tell the whole story, but the graph can, as far as it goes, stand alone. So you need these proper labels, the way we set it up. You also need a title. Right? So for this one, it would be the effect of changes in pressure on volume of methane. Okay. The other one would be the effect on the volume of a gas by the change in temperature. You need a title. Okay. Those are the things that I'm looking for when you present your completed report. Okay. I think that we've covered most everything. Just a second. And I'll take a quick look and see, be sure I don't miss anything. You know how to calculate the slope, that's good. Let's see. Okay. The very last, in the bonus section, the very last problem, we didn't look at that one, is a doozy. So you can try it, but I'll give you a hint. The graph of the data in the last one that we didn't look at, let's just go down there and take a quick look at it. Okay, here we go, right in. Here it is. Okay, so for this one, you're going to get what's called a broken curve. So you're going to have actually a line for part of the graph, and then it's going to abruptly shift to another part of the graph. Okay, so that could spin your head around. And if you want to attempt this type of problem, I have no problem with you going to the internet and looking up similar problems to see how they're approached. That's a sign of curiosity, right? This is not an exam where you're limited. You can't bring in anything from outside. This is like a research project where you go and look and see what's been done elsewhere to help you understand the data. Okay, so you can go research this one if you want. Okay, so I've said enough, and we've covered all the topics. So good luck. Stop the share and stop the video.